Well, I'll say good morning to everyone, although I feel like saying good evening because it's actually 11 p.m. my time. But I had a fantastic time in China. I ate like a pig. I gained 4 pounds. It was fantastic. But then, is that mine? Oh no. Should have shut that off. Yeah, my son is calling me. Anyway, while I was over there, I got an email from American Airlines saying my flight was canceled. But they said, don't worry, they could get me back today at about 11 o'clock. But that wasn't good. I was going to miss my class. So anyway, I got on a different flight. I had to spend 12 hours in the Shanghai airport waiting for the different flight, but I got it and made it back here. So this is a new homework, and here's the old homework. Please pick it up. It's so heavy to carry it back and forth upstairs. So pick it up after class. So I think, well, maybe I should ask, I had recorded 2 classes. Any questions on the 2 classes that I had recorded? You've all watched them, right? So I think the last class that I recorded, I just started here on phase stepping and phase shifting. Maybe I've shown a couple of the slides here, but let me go back and begin here at the beginning of this section. What this is really a technique for getting interferogram data into the computer. Computers have changed everything that we do, and for the most part, it's made everything better that we do. And it certainly has made interferometry a lot more powerful than what it was before. Being able to get the data into the computer and then all the analysis you can do on the data is just added to the capability so much. So we need a good way of getting the data in, and this is what we call phase stepping, or more often it's called phase shifting, and I'll explain the difference between the two. But it's just a very, very superb way of getting data into the computer. So we're going to talk about this a fair amount. We're going to see that all these systems need a phase shifter, and so we'll talk about different phase shifters. We'll talk a little bit about the different algorithms. We'll talk about phase unwrapping, explain what we mean by that, phase shifter calibration. Of course, there are errors present, so we'll talk about these. And then the biggest error is really error due to vibration. And so we're going to talk about ways of getting around these errors due to vibration. So this phase shifting, phase stepping, will work with any 2-beam interferometer that you have. And so I show here the basic Toyman green. And so we're going to get an interferogram down here. And we're going to put a solid state detector array down here and interface that to the computer. And we're going to read out 3 or more frames of the data. And I say 3 or more because there are 3 unknowns here that we have. We don't know the irradiance of the test beam. We don't know the irradiance of the reference beam. And we don't know the phase difference between the 2 beams. And so there are 3 unknowns. And what we want to solve for is the phase difference between the 2 beams, because that's going to tell us what's wrong with the test optics, what we have to do to fix the test optics, or we can calculate just how well the test optics will perform if we don't fix it. And so, I mean, the test optics, I show it here as a simple mirror, but it can be a mirror, a lens, a complex optical system, whatever, spherical, asphere, whatever. And so we're going to take 3 measurements, and then there's going to be a little calculation here from which we can calculate the phase difference between the 2 beams. And we'll look at different algorithms for doing that phase difference, and maybe some advantages and disadvantages of the different algorithms. So this phase shifting is really a very powerful. It's going to enable us to make measurements down in the angstrom or even sub-angstrom range. It's, when we're trying to find the centers of the fringes, maybe we could do the measurements to 1/10 of a fringe. Here we can do it to a fringe divided by 1,000 or more than 1,000 even. And it's going to be really fast. And of course, as computers have gotten faster over the years, it's gotten much faster. It's going to work well with high contrast fringes or low contrast fringes. We might lose a little accuracy if we have low contrast fringes, but we're probably going to still get pretty good results. And it doesn't depend upon the intensity of the beam being constant across the beam. It can vary across the beam, and it still works well. We're going to get the phase at a fixed grid of points. We're going to have some detector, which nowadays might have a 1,000 by 1,000 element array, or even larger than that. So maybe it's 1 million data points that we're measuring the phase at. And it's going to work well with large solid-state detector arrays, as I said, 1,000,000 by 1,000,000, or 2K by 2K, or even larger. So in all of these different ways of doing the phase shifting, some way we have to introduce a phase difference between the two interfering beams. And there are many ways of doing this, and we're going to talk about a few of them here, starting off with a moving mirror, and then a diffraction grating, and a Bragg cell, and a couple of different polarization techniques, Zeeman laser, and then a frequency shifting source. So we start off with the one that is the most commonly used. And that's just, maybe our reference mirror is mounted on a piezoelectric transducer. We apply a little voltage to the PZT, and the PZT will expand or contract and move a small distance. And so the beam's coming in. If we move this 1/8 of a wavelength, the path will change by, twice that, or 1/4 of a wavelength. And so that's introducing a 90-degree phase shift in this reference beam. This technique, as I said, is probably the most common way of doing phase shifting. And its reason for that is, first off, it's easy to do. You just take any of your interferometers and you mount the reference mirror on a PZT. A PZT has very nice motion, and actually pretty linear motion. If it's not linear enough, you can calibrate it to see how much voltage you have to apply to get 1/8 of a wave. But it's generally pretty linear, very smooth motion, and it's a great way of doing the phase shifting. And as I said, the most common way. But it's not the only way that people do. Another way that I have had a lot of fun with over the years, and that's using a diffraction grating. And so if we think here that we'll put in our diffraction grating, illuminate it with a beam, we get a 0 order going straight through, and we get a 1st order coming out here. Now, if I move the grating sideways, or if I have anything and I'm taking the Fourier transform of it, and I move it sideways, how does the Fourier transform change? Does a linear phase shift? And so the order isn't, the amount of light in the order is not going to change, but the phase of the order will change. And as you move the grating sideways, the phase shift, if you go back to your Fourier transforms, the phase shift will be proportional to how far I move the grating. And it's going to be proportional to the spatial frequency. And if you go through the math, and it sort of almost makes sense here, if I move this 1 period, the phase of the first order will go through a phase change of 2 pi, 360 degrees. The minus first order, how much will the phase of the minus first order change by? That's proportional to the spatial frequency. It's going to be minus whatever the plus first order was. So if we move this 1 period, the first order changes by 2 pi. The minus first order would change by minus 2 pi. The second order would change by 4 pi, and so on. So if I'm looking at the first order here, if I move this a quarter of a period, then the phase of the first order will change by 90 degrees, a quarter of 360, or pi over 2 phase. And a minus first order would change by minus 90 degrees. And a zero order phase will not change. And so you can think of having an interferometer where the one of the beams goes through the grating, either reference or test beam. And if you just move the grating sideways, then you'll get a phase shift of the beam. And the nice thing about this is that the phase shift is independent of the wavelength. You know, if I go back here, I said, well, if I move this a certain distance, if I move it 1/8 of a wave, then I'm changing the phase by 90 degrees. But if I change the wavelength and keep the distance that I move it the same, the phase shift would be different. And so for a given motion of the mirror, the phase shift depends upon the wavelength of the light. While here, if we change the wavelength, of course, the first order comes out at a different angle. But as we move the grating sideways, the phase shift of the first order will be independent of the wavelength. Yes?
If you wanted to use this method in a quantum interferometer, would you put a blaze grating in the reference arm? Is that a possible way to do it, or what would be how you, like, where would that go instead of?
There are many places where you could put this, and let me see. Yeah, okay. I'll show you my favorite in about 2 slides. But I mean, you could put it in a reference arm, and a blaze grating is nice because you get much higher efficiency. But it doesn't have to be a blaze grating. But in a minute, I'll show you my favorite place to put it. Well, another way of having a moving grating really would be an acousto-optic Bragg cell. And so here what we do is we drive this at some frequency, maybe, I don't know, 30 megahertz or something. And what we set up then will be a traveling wave across here of index variations in the Bragg cell. And so that's like a moving grating, phase grating in this case, so we can have a very high efficiency. And so the beam comes in here, and one beam is zero order, goes straight through, and we'll get a diffracted beam out here, first order. But this is a moving grating, and it's moving at a rate of f periods per second. And so we're getting a phase change, and that phase change is going through 2 pi f times per second. And so what we really have here is a frequency change of the light. Just like if I came back here, I mean, if I were to move this sideways at a constant rate, and let's say I moved it at 10 periods, 10 grating periods per second, then we would have frequency shifted this by 10 hertz. And we would have frequency shifted to -1 order by -10 hertz. And so we have the same thing here. We have a traveling wave going across here. And so the first order is being frequency shifted by whatever frequency I'm driving this at. Okay? And I like this very much. Well, I should go back here and say, while I love this, I hate mechanical things. I hate things that move like this because they break. and I'd probably have asked you before, do we have any mechanical engineers in the class? Because I'm going to insult mechanical engineers all the time during the semester, so I get myself in trouble here. But mechanical things always break. This is really nice. This is just more of an electrical thing. Not that electrical things never break, but this is just a very, very clean way of getting a frequency shifted beam that we can use in our interferometer. And we could put this in the reference beam, as we said before. We could put it in a test beam, or my favorite way of using this, and it's the same as for the grating, is the following. So over here on the left, I have some interferometer, and I don't know what it is. It doesn't matter. It's a 2-beam interferometer, Twyman Green or whatever. But I range it so the reference and test beams come out here at some angle relative to one another. And so let's say the reference beam comes out here, and it's diffracted up here at this angle. And if I'm driving this Bragg cell at a frequency f, then this is frequency shifted up here by frequency f. And I've arranged this angle here to be just right so that the 0 order for the test beam comes out at the same angle as the first order for the reference beam. And so these two will differ in frequency by f. And so if I were to put a detector here, detecting the fringe pattern, I mean this is a beam of some size, I could have a detector array here. But anyway, if I just put a detector here, these two beams interfering, the radiance will be changing in frequency at the difference frequency here, or f. Okay. And if I look down here, now I have the test beam is being diffracted down here into a minus order, and my reference beam is coming down here at the same. And so the test beam is at frequency f0 minus f, and the reference beam is at frequency f0. And so again, I could be looking at these two beams, the interference here, or I could be looking up here, either one. So this would be my favorite way of putting in the Bragg cell or putting in the diffraction grating. The nice thing about going back here to our diffraction grating, a problem. Well, no, I won't. I'm not going to talk about that. I'll talk about that later, I guess. I'm not ready to talk about it yet. Okay. So anyway, this is a very good way of using a Bragg cell as this case, a frequency shifter, which is just a phase shifter where the phase is changing at a constant rate. So any questions on this? Okay. Well, I will say one thing here, that if I have, have windows on this, or if our grating is on a substrate with some thickness variations, here both beams are going through that, and so I'm not getting errors by thickness variations in the substrate to the grating or the windows on the Bragg cell here, because both beams are going through it. Okay, the next, there are a series, well, I'm going to show two of them, I guess, of polarization phase shifters. And this is going to be what we call geometrical phase shifters, and they're kind of interesting, I think. Now, I think all of you are experts on Jones calculus. We've at least mentioned it in class before, and I assume you have noticed on the website here that we do have. If I can get it anyway. We do have a table here of the different Jones vectors that we will use. and Jones matrices that we will use. And I mention that because that just, like if I pick QFAV, that's a quarter wave plate with a fast axis vertical. So that's these symbols here that we're going to see in just a minute. And then the rotation matrices if we want to rotate any of these elements, which we will. Okay, so that takes me back here to looking then at a rotating half-wave plate and then a rotating polarizer as a phase shifter. So here's another technique that I've found a lot of use for over the years. So let's say the reference and test beams have orthogonal polarization here at 0 degrees and 90 degrees. And we've looked at interferometers for polarization type interferometers for getting that. Now in the output beam then, so the test and reference are coming out here, we're going to send that through a quarter wave plate oriented at 45 degrees. And so that's going to make both these beams have circular polarization. One will be right-handed circular and the other one will be left-handed circular. So after the quarter wave plate we have a left-handed, right-handed circular. This is going to be a half-wave plate, and we're going to rotate this half-wave plate. That's going to produce a phase shift. We'll see in a second here. And this will, so we're going to rotate at some angle theta here. Let's see, what does a half-wave plate do to circular polarization? Right, it's going to change right-handed to left-handed and left-handed to right-handed. It's also going to introduce a phase shift, but we'll see that in a minute. So we still have right-handed and left-handed circular here. And then we'll put these through another quarter wave plate. And so that's going to take these left-handed, right-handed circular and produce that linear. So here we're going to, just like here we had two linear polarizations, here we're going to have two linear polarizations at orthogonal directions to one another. And so we won't see any interference. And so we put in a polarizer here at 45 degrees, and we will see interference. And what I'm going to claim, and we'll go through the math, or look at the math in the next slide, what I'm going to claim is that this interference pattern, the phase of that interference pattern, is going to depend some way upon the rotation of this here. And it's going to turn out, we'll see in a second, that if I rotate this at angle theta, the phase of this interference pattern will change by 4 theta. It's going to turn out. So going back to the Jones calculus here, we could write the input as linear polarization, and there's some phase difference between the two, which is phi. And so the whole goal here eventually will be to measure what phi is, but right now we're just going to do phase shifting. So this is our input, and then we had put that through the quarter wave plate. The quarter wave plate here at 45 degrees. And so that's here. And then we put that through our rotation, our half wave plate that we're going to rotate at an angle theta. And then I put that through another quarter wave plate, but now that was at minus 45 degrees. And then we put that through a linear polarizer, and we get some output here. And I want to find the intensity of the output, so I take the output, multiply it by its complex conjugate, and lo and behold, what we get here is our interference pattern with cosine of the phase that we eventually want to measure, and then another phase here of 4 theta, where theta was the angle of that half wave plate. And so as we see, if we rotate the half-wave plate and angle theta, the phase difference between a test and reference beams changed by 4 theta. Okay. Any questions on that? So there are at least a couple ways you could do this. I could put this in the output of the interferometer where the test and reference have orthogonal polarizations. Or I really could have put this in the input source. And so I could have put in, I could have a source here, polarization say at some angle here, or I could adjust the angle to eventually adjust how much light I have in the 2 orthogonal directions. And I could have gone through to this point right here. And remember right here we said what we have are 2 orthogonal polarizations with some phase difference between them. And so this could have been the input. Just take the first 3 here. This could have been the input to the interferometer, to a polarization interferometer, because now I have polarizations at linear polarized light at 0 degrees and 90 degrees, and I have a phase difference between the 2 that I could control here with this half-wave plate. And so that could have been the input to a polarization type interferometer. So it could be used as an input or as more often used as the output. Okay. Any questions? Then we'll now come to what is nowadays my favorite phase shifter. And in a couple, 3 classes, you'll see why I say that. But it's the following. It's saying, let's say that, again, the reference and test beams have orthogonal polarizations at 0 and 90. I put in a quarter wave plate at 45 degrees. And so now I have what, left-handed and right-handed circular. And now I'm going to put in a polarizer to get interference fringes here. And what we're going to see in a second is that the phase of these interference fringes depends upon the orientation of this polarizer. And if I rotate the polarizer an angle theta, it's going to end up at the phase difference here, or the phase in the interferogram changes by an amount 2 theta. So let's look at the Jones calculus for that. So again, this is my input, linear polarization, and the phase phi we want to measure. And then I put this through my quarter wave plate at 45 degrees. And then I put that through my polarizer here. And, oops, better get the right direction here. My polarizer here, but I'm rotating that some angle theta, so I put that between my 2 rotation matrices. And so that gives me my output, and I want the intensity, so I take the output times the complex conjugate of the intensity. And so I'm going to get something down here that a sine in this case, could be a sine or a cosine, but a sine here, way I've written it, with a phase in it that I want, and a phase here that is changing by twice the angle that I rotate my polarizer. So we could just take our polarization interferometer and the output, put in our quarter wave plate to get left-handed, right-handed circular polarizer that I could rotate, and I do my phase shifting by rotating the polarizer. And again, the phase shift is independent of the wavelength, depends only upon the angle at which I'm rotating the polarizer. That's pretty nice. And in a couple of lectures, I'll show you how to make very good use of this technique for phase shifting. So any questions on that? Another technique that's used is a laser that we put in a magnetic field to get Zeeman splitting, and I think we briefly mentioned that in class a couple of 3 classes ago. And so it ends up, we get 2 frequencies out of this laser. The 2 frequencies have orthogonal polarization, and so again, this could be used as the input to our polarization type interferometer, where one of these frequencies would go with one state of polarization would go along the test arm of the interferometer, and the other frequency with the other orthogonal state of polarization would go along the reference arm of the interferometer, and we'll be able to do our phase shifting, as we'll see in a little bit. So that's a nice clean way of getting the 2 frequencies again, no moving parts, which I always like, and that has been used quite a lot over the years. Okay, the last one here is one that I only recently added to the notes. And in a second, I'll tell you why it took me so many years to add this. But if we think here for a second, the phase difference between, for these 2 paths here, goes as 2 pi over the wavelength times the path difference, the round-trip path difference, that is. And I could rewrite that as 2 pi over lambda as 2 pi nu, the frequency, over c, times the path difference. And so if I were to change the frequency of this laser, I'm going to get a phase difference here. And so if I change the frequency by what I call just frequency shift, then I'm going to get a phase shift that goes as 2 pi over c times the frequency shift times the path difference. Now if the paths are matched, well, I'm in deep trouble here, because I don't get any frequency shift here, I don't get any phase shift by changing the frequency. And so, of course, this is only going to work if I have a path difference. And the frequency, or the phase shift for a given frequency shift, will become larger as the path difference becomes larger. Now, I've known about this since the beginning of time, it seems, but I only added it to the notes recently because for years I thought this is a terrible way of doing phase shifting, because your phase shift is going to depend upon your path difference, and that's going to, if for some reason I change the path difference, I'm going to have a different frequency shift to get the same phase shift. And that kind of bothered me, so I thought it wasn't very useful. But then one day I got thinking here. I always talk about these stray reflections you get in an interferometer, give you spurious interference fringes, and maybe from an academic viewpoint you almost don't worry about that. But I tell you, if you're making interferometers that you're selling, these stray interference fringes just drive you crazy, because they always introduce error. And it's so hard to get rid of. You try to put on good coatings, and you try to spatially filter, and you do everything you can to get rid of these stray interference fringes. But you never can get rid of all of them. But I realized here, these stray interference fringes, the light making up these fringes probably will have different path differences. And so the phase shift for these stray interference fringes will be different from the phase shift between the 2 beams that you want to measure. And so maybe they don't bother you so much. And it turns out to be the case. In general, they don't, yes.
Would this be a good way to measure distance with interferometer?
Yeah.
Because you could get the path difference.
Oh yeah, this is a way of measuring distances, and chirped radar works this way. But it's you just change the frequency, you measure the phase, and from that you get a distance. That's a good idea, yes.
And another thing I was wondering, if you're testing an optic that's not a perfect null test, doesn't the path difference change across the optics?
Well, from each fringe to the next, it changes by one wave, yeah.
It's just not enough.
It's not enough no, it's not enough. But it is enough to reduce the effects of some of these stray reflections in the system. And so this is not such a bad idea at all for doing phase shifting. Now I've played with this in a lab a fair amount, but we've never sold an interferometer based upon this principle here. But it is actually not such a bad idea after all. Okay. Any other questions? This is the end of the phase shifters I want to talk about. You can come up with other ones, I'm sure. In fact, it'd be fun for you to think about other ways invent other ways of doing phase shifting or frequency shifting. Sort of the same. Okay. But these are the most commonly used ways. So now what I want to do is to talk a little bit about algorithms, and we'll get to real phase shifting or phase stepping here. And so we start off here with the equation that you all dreamed about last night. Did anyone dream about this equation yet? You haven't seen it enough. You know, when I was in China, I was talking to, I don't know, 100, 200 students, something like that. So I asked them if any of them dreamed about it the night before. Not a single one had either. But anyway, maybe that night they did. I don't know. But so our basic equation for two-beam interference. And we have the phase here is two different phases. We have the phase due to our phase shift. I just call that phi of t, because right now anyway we're changing phase as a function of time. And then we have what we're trying to measure, the phi of xy. And so the whole goal here is to measure phi of xy. And so what we're going to do here is that if I set phi of t be equal to 0, then we just have that our irradiance is I sub dc plus I sub ac cosine of the phase, phi of xy. And so this is falling on our detector array. We're going to have some solid state detector array in the output of the interferometer. And going to be interfaced to a computer. And we're going to read out this array. So let's say we have a 1,000 by 1,000 element array. And so we're measuring this irradiance here at 1,000,000 data points. So we'll read out the array, store that in computer memory. And now we'll change the phase by another 90 degrees, or by 90 degrees, I should say. And so I put 90 degrees in here, and the plus cosine becomes a minus sine from our trig identity. And so again, this falls on our detector array. We'll read out our detector array and store this, another 1,000,000 data points of the intensity here, or irradiance. Change by another 90 degrees, put 180 in here, so now this becomes a minus cosine. We have this irradiance falling on our detector. Read that out and store it in memory. And I really could stop at this point here because, we have three unknowns. As I said before, we can think of, we have the intensity of the reference beam, intensity of the test beam, and the phase difference between the two are the three unknowns. And, or in this equation, we have I sub dc and I sub ac, and the phase here unknown. I'm claiming I know what the phase shift is. We'll worry about that in a little bit, but right now I'm claiming I know what that is. But I like the number 4, So I'm going to do another one here. And maybe in a little bit I'll tell you why I like 4 better than 3. So now this minus cosine becomes a plus sine. Again, this falls in our detector array. And we'll read that out and store it in memory. And now, for each detector point, I'm going to find the difference between I4 and I2. So the I sub DC's cancel. And I'm left with a 2 I sub AC sine of the phase up here. And downstairs, I1 minus I3. I sub DC cancels, and I'm left 2 I sub AC cosine of the phase. So we have the sine over the cosine or the tangent of the phase. And that's it. Now, isn't that simple? Well, the first time I noticed this was a long time ago, before you were born. It was like 1969 or 1970, something like that. And I thought, you know, this is so simple, it can't be worth anything. But the truth of the matter is, this is so simple, and that's why it's worth so much. It's just a very simple way of calculating the phase. And at the time when I thought of this, I mean, the real problem back then, 1969, 1970 time frame, was that we didn't have solid-state detector arrays. We didn't have personal computers. And so this equation was simple, but to implement this in an interferometer was not very simple. And we did build one. I was working for a company in the Boston area at the time, and we built this on a classified project. We built one of these where, you know, nowadays you have 1 million detector points, or 4 million detector points, or 6 million detector points. The one we built in about 1969, 1970, we had 21 detector points, discrete little detectors. We had a huge rack of electronics. I mean, it was really a complex thing, and it wasn't very practical, I'd have to say. And the only way we got to build it, I mean, we did it on a classified project where we had lots of money, because it took a lot of money to build one of these systems back then. And it wasn't very useful. But it, you know, another maybe 15 years later, personal computers became available, solid-state detectors became available, and it became very useful. And nowadays, essentially all interferometers used in optical testing work along something like this. You know, it may not be 4 steps, it may be 6 steps or 8 steps or something like that, but it's all the same basic idea. This has just turned out to be such a good way of getting interferogram data into the computer. So you have the tangent of the phase, and so now you can just take the arc tangent and find the phase. And if you're testing something, say a mirror at normal incidence, then to get to the height error, you just take the phase and you divide that by 2 pi, and you multiply that by lambda over 2, and you get the height error. And so, you know, you take all these measurements in a fraction of a second, and you have the height error of this sample you're testing at 1 million data points. I mean, it's just pretty simple to do nowadays. So this is really what I would call phase stepping, because we're changing the phase in discrete steps here. In a little bit, we'll modify that to get to what I call phase shifting. Okay, so if, you know, this is one algorithm. If you look in the literature, you're going to find, I don't know, hundreds of different algorithms that people will use to calculate the phase. But they're all somewhat similar to that. And the next slide here will show just some of the algorithms. I mean, and they're pretty easy to calculate, to derive. I'm not going to do it in class, but they're pretty easy to do. So he said we have 3 unknowns, so we only need 3 measurements. And so we can use this algorithm up here. What is that? I3 minus I2 over I1 minus I2. And again, it's basically just looking at the sines over the cosine. And again, these are 90-degree phase steps. And why do we use 90-degree phase steps? We do it because the algebra is easier, basically. We get just sines and cosines by using 90 degrees. If we used 87 degrees, it would still work, but the algorithm would be a little more complicated, but it still would work fine. Why do we use 4 instead of 3? And I'll talk more about that later, but it turns out that 4 steps will be a little bit less sensitive to the phase steps being exactly 90 degrees than what 3 is. Okay. The next algorithm here is what I call the Sweeter-Harahan algorithm, and that uses 5 steps. And that turns out to be a very, very nice algorithm that is not too sensitive to the steps being exactly 90 degrees. In a little bit, we'll look at a nice simple way of deriving that algorithm here. Now, I should say I used to call this the Harahan algorithm. And one day I got a letter, not an email, I actually got a letter in the mail from Sweeter, who said, "Why do you call that the Harahan algorithm?" Says, "I derived that and published it years before Harahan did." And he gave me the reference. I went back and looked, and sure enough, he had published it a number of years before Harahan did. So anyway, now I call it the Sweeter-Harahan, and that has become pretty much the common name for this particular algorithm. And we'll look at it in more detail in a little bit because it's a very nice one. Then we have this thing down here called the Carré equation. Now, the Carré equation is nice in that this works almost independent of what the phase shift is. It doesn't have to be 90 degrees. And these 3 up here, we're assuming that we have 90-degree phase steps between adjacent measurements. This can be essentially anything. I mean, it can't be 0, but it can be about anything other than 0 for what the phase steps are. So that's kind of nice. And so you would think people would only use this. I mean, why not? Well, and it's 4 steps. But the reason that it's not widely used is that this one is, while the steps can be anything, it's very, very sensitive to the steps being 90 degrees. Excuse me, to the steps being, I think my mind is still in China maybe, to the steps being equal. They can be anything, but they have to be equal. And if they differ just a tiny little bit, you get a fairly large error. And so because of this, it's essentially never used because of that. Now, Carré, at one point in my life, I thought I was the first one to come up with phase shifting, but it ended up that Carré actually had done this 4 or 5 years before I did. He published it in a journal in French, which is my excuse for not having read it. Many years went on, we were using phase shifting, other people using phase shifting, and then someone finally found that equation. And so Carré is really the first one to come up with the idea of phase shifting or phase stepping. Okay. We're going to talk more about deriving these algorithms in a little bit here. But before I do that, I want to talk about, sometimes I say phase stepping, and sometimes I say phase shifting. And the literature, for the most part, calls all this phase shifting. But there is a difference, in my mind, between phase stepping and phase shifting. So phase stepping what we're doing is we are changing the phase doing a measurement. Changing the phase doing a measurement, and so on. And so if I'm doing my phase shifting or phase stepping by moving a mirror, you know, I have the mirror, the reference mirror is at a certain location. I get the intensity pattern, I read it out of the detector and store it. Then I move the mirror to another position, another phase shift. I measure my intensity and store that in the computer. Move the mirror, measure the intensity, store that in the computer. So we're stepping the mirror, stepping the phase. Now, a practical problem is that, you know, I do a measurement here. Now I move a mirror. Well, it takes a little while to move the mirror, and then it takes a little while for it to really settle down. So I have to wait a little while before I read out my detector. Then I'll move the mirror and wait for it to settle down, and then I'll read out my detector and so on. So it's going to take, say, let's say each exposure is, I'll say a 30th of a second. Then I probably have to wait another 30th of a second before I can do my next exposure and so on. So it's going to take a little longer to take the data than just the time required to expose the light to the detector. I'm going to have to do some waiting in between the readouts here. So that's phase stepping. Phase shifting is that we're going to move the mirror at a constant rate. We're going to be changing the phase at a constant rate, sort of like a frequency shift. Okay. Now, if I'm changing the phase difference at a constant rate, my intensity pattern is going to vary sinusoidally with time. And so what I'm really doing is I'm integrating the light intensity as the phase difference changes by 90 degrees. And so I'm going to be integrating the intensity under this cosine as the phase changes by 90 degrees. And then I'm going to read out the detector very fast. And then I'm going to integrate the intensity again while the phase changes by 90 degrees. And repeat this, you know, 3, 4, 5, 6, 7 times, whatever. And so this is integrated bucket or phase shifting. The advantage here is that I can take the data fast. I don't have to wait for the mirror to settle. I can just get the mirror moving, and then I can take the data faster. Or I can be using one of these frequency shifters that we talked about before, the Bragg-Zell, the Zeeman split laser or whatever, where I have a frequency shift between the two beams, and so I'm getting a sinusoidal intensity pattern with time. And so this is phase shifting, this is phase stepping. In the literature, they essentially call everything phase shifting. Any questions on that? Well, one question you might have, I was hoping you would have, I mean, here I'm integrating the light essentially as the fringes are moving. You know, I've set up a phase shift between the two beams as a function. You know, it's changing at a constant rate, and so the fringes are really moving. Or if I look at the intensity at a given point, you know, I have something that's varying sinusoidally with time, and so this is sort of tending to smear out the fringes, wash out the fringes, reduce the contrast of the fringes. Does that make any difference or not? Does that bother you? Does it make a difference? Yeah. Well, it probably doesn't make too much of a difference, so we wouldn't be doing it all the time. But let's see how much difference it does. So what we have our two beam interference fringes, and we have a phase that is varying with time, and we're integrating this intensity over some time or over some phase change. And if I go through here and go through this integral, which I assume everyone's going to go back to your office and do, what you end up with is I get something down here that has my sinusoidal fringes like I want, but the contrast is reduced a little bit, which makes sense because I'm integrating this as the phase difference between the two beams changes by a little bit. So it makes sense that the fringe contrast is going to be reduced a little bit. And it's reduced by a sinc function here. And it's a sinc of delta over 2, where delta is how much the phase is changing by while I'm integrating the intensity. So if I'm integrating the intensity as a phase shift, as a phase difference changes by 90 degrees, pi over 2, what this is here is a sinc of pi over 2 divided by 2, or the sinc of pi over 4. In phase stepping, I'm not doing this integrating as a phase difference between the two beams changes. And so for phase stepping, delta is 0. For integrating bucket, delta is, well, typically pi over 2, 90 degrees. And so the sinc of pi over 2 divided by 2, or the sinc of pi over 4, just happens to be about 0.9. So the effect here is that we're reducing the fringe contrast by about 10%. So by integrating over a period of time while the phase changes by 90 degrees, we're reducing the fringe contrast by about 10%. So what this is saying, and I still end up with nice sinusoidal fringes down here. So if I'm going to derive equations for phase stepping or phase shifting, the equations to determine the phase are exactly the same. There's no difference between phase stepping and phase shifting. The only difference is that we are reducing the fringe contrast by about 10% by using 90-degree phase steps, shifts. Okay. And we have the big advantage that we can take the data faster here if we use phase shifting, faster than when we use phase stepping. And so most commercial interferometers will use this approach here of phase shifting. Only penalty is small reduction in fringe contrast. We can take data faster and well worth it. Okay, any questions on that? Okay, well, we have all these algorithms here. And I mean, the way, if it's, you want to calculate for 5 steps or 6 steps or whatever, I mean, you can go through some procedure like this and you simply write this out. The nice thing about using these 90 degrees phase steps is you get nice sines and cosines here. And so it's not very difficult to calculate what these algorithms are, at least if the phase steps are 90 degrees. It becomes a little more difficult if they're not 90 degrees. And, but it's not that hard to do. But there's another way of doing this, another way of looking at this that turns out to be very nice. So another approach for calculating phase shifting algorithms. So we have two-beam interference. We have, I'll write it this way as I average times 1 plus gamma cosine of the phase difference here. Gamma then is to take into account that then two intensities are not, the intensity of reference and test beams are not the same, or maybe the polarizations are not exactly the same, or the coherence is not perfect. Or, you know, in phase shifting, we have a sinc function here. So anyway, some gamma here, cosine of the phase we're trying to measure plus my phase shift delta. So phi plus delta. And I could write this if I wanted to. This is a cosine of a sum here. If I go back to my trig identities, I could write this as a cosine delta, cosine phi, minus a sine delta, sine phi. So just expanding the cosine of the sum as to a cosine, cosine, minus sine, sine. Well, you might say, why do that? It looks more complicated. Well, we'll see in a second here. Then I could say, I could look at this and I say, well, let's let A naught, or A naught here, be I average. Okay. Now let's let A1 be I average gamma cosine of the phase that I'm trying to measure here. And let's let A2 be minus I average gamma sine of the phase. Okay, no reason why not do that. So then I could rewrite this expression here as the radiance is equal to A naught plus A1 times cosine delta. Remember, delta is the phase shift I'm introducing, plus A2 sine of delta. Okay, well, okay, just bear with me. It may seem crazy to do it this way, but you could do it this way. And then I could say, well, you know, if I think here for a second, tangent of the phase is simply minus A2 over A1. Okay. And gamma, which I may or may not care about, but I might as well write it down here. I could solve for gamma here. It's the square root of A1 squared plus A2 squared over A naught. Okay. So if some way I determine A1 and A2, I can determine the tangent of the phase. Always just tangent of the phase minus A2 over A1. Okay. Well, still seems kind of crazy, but why would I want to do this? Well, this leads to something here that is fantastic. Least squares fitting to determine the equations here. This was first introduced by a man by the name of Morgan in an article many years ago, and I've never met Morgan. I don't know who he was, but it's really great. So we just kind of, a lot of words. Boy, that's a terrible slide. That's a slide shows you how not to make a slide with so many words on it, but let's look at it anyway. So first off, I mean, we have to have at least 3 phase shifts. And I could have, there's so many ways you can see that, you know, you have 3 unknowns, and so you have to have 3 measurements. We've said that many times. Now, if the measurements are performed for 3 phase shifts, then it's possible to solve for A1 and A2, and the phase phi's can be determined as a function of position across the pupil. So, I mean, that's true. If I do 3 phase shifts, I can I'd have this equation here. I do the measurement at 3 values of delta here, and so I'm going to have 3 equations for the 3 deltas, and I can solve for A1, A2, and A naught if I want. And once I know A1 and A2, I can solve for the tangent of the phase. Okay, so what? Okay. Now we get to the good part. What if we have more than 3 phase shifts? Well, then we can solve for A1 and A2 using the least squares approach. And all of you have done things using least squares, but let's just repeat just how we would do that. And so remember, in least squares fitting, you find the square of the difference between the measured irradiance and the irradiance calculated using the above expression we had here. Okay, so we simply are going to, we have our equation here, and we're going to measure the irradiance, And then we're going to find the difference between the measured and the equations using, well, take the difference and find the square of the difference. And then we're going to take the derivative of each of these with respect to the three unknowns, equating these results to 0, and then we're going to end up with three equations that we can solve for A1 and A2 and A0 if we want. So it's just a typical least squares fit approach, and we can very easily solve for the phase then. And it turns out that the equations you get using this least squares approach, I mean, if I did it for 4 steps, and I have some additional notes on the web where I show for doing that, I get the same equation that I derived before. If I want to do 10 steps, I mean, I can just, set up, do these 10 measurements, find the difference between the I calculated here and the measured, square that, take the derivative of that with respect to A0, A1, and A2, and solve for this to get my equation, to get the phase. It's just a very simple, that will work. It no longer has to be 90-degree phase steps. It can be whatever. They don't have to be equal phase steps. They can be whatever you want, and you can just solve very easily using the least squares fitting. It's just a very, very powerful technique. Okay. Any questions at this point? Again, I have more notes up on the web you may want to look at. I have a what came from a Mathematica notebook where I go through a lot of least squares fitting to solve for the equations for different number of phase steps.
Is everybody using this algorithm now?
What's that? Everyone? Yeah. The least squares? Yeah. It's common. I won't say everyone uses it, but it's common. Yeah. In a little bit, I'll show you what is probably most which is used most of the time, but it drops right out of the least squares approach. It's just, I don't know, it's just so elegant. It's just, it's so simple to do, and works so well. Well, before we go on, there was one more problem I kind of skipped over here that I should mention here. That we're calculating the tangent of the phase, and I don't care how many steps you use, you're always calculating the tangent of the phase. And then we're doing an arctangent. And this arctangent then goes over a range of 0 to 2 pi. So we're measuring the phase only over a range of 0 to 2 pi. Now let's say I'm measuring something that's varying by a lot more than 2 pi. For example, I might be measuring a spherical surface. And so between fringes, the phase changes by 2 pi. And if I have several fringes present, then I have, phase change of many times 2 pi. And if I were to plot that, it would look nice like this. But when I go through my arctangent calculation, I'm only getting the phase between a range of 0 and 2 pi. And so instead of measuring a nice smooth surface like this, what I measure is something that goes from 0 to 2 pi, down to 0 to 2 pi, and so on. Sort of like a sawtooth here. So that's not good. Some way I have to correct for these phase errors, phase jumps, phase ambiguities, whatever you want to call them. And so the problem here, as I said, I'm measuring the phase only over a range of 2 pi. So what we do here is now I'm going to have to put a restriction on how fast the phase changes. And this turns out to be a headache that we're going to see a few times this semester. I'm going to require that between adjacent detector pixels, the phase changes by less than pi. So that is saying that I have at least 2 detector elements over a fringe. I'm sampling a fringe at least 2 times per cycle. So it's sort of like the Shannon sampling theorem that you probably have heard of. So this is going to put a limit on how steep a slope I can measure. Between pixels, the phase difference has to change by less than pi. So what I'm going to do here is I'm going to trace my path going across the fringes. And I'm going to, whenever the phase jumps by more than pi, I'm going to add or subtract some integer number of 2 pi's, so the phase difference is less than pi. So what does that mean here? So I'm measuring something like this. You know, it ends up something like this. Now I have these steps here that are 2 pi. So whenever between pixels I have a step that is greater than pi, I'm going to add or subtract some 2 pi's to make it less than pi. And so that way I can build up my smooth surface. And so instead of getting something that looks like this, I'll get a nice smooth surface that looks like this. Okay. Well, this is maybe easy to explain, but in practice it's harder to do than what it is to explain, because you always have a little bit of noise. And so it's very easy to have the noise make the step appear to be more than pi when it's actually less than pi, or the other way around. And so this takes a fair amount of intelligence to take care of the noise problem. A lot of work over the years has gone into this, not just for phase shifting, but it's used in a lot of different areas. And there's a superb book here, an inch thick or so, describing what I described in one view graph. And so maybe I didn't tell everything in a one view graph. But if you ever get into this phase, what they call phase unwrapping problem, I strongly recommend this book. It talks about the different algorithms for doing it. So I think I'll stop at this point. Time is about up. Maybe I'll come back next class. I'll say just a few more words about the phase unwrapping then, and then we'll go on to phase shifter calibration and a little more on algorithms and so on. So don't forget to pick up the old homework here. And if you haven't handed in your new homework,